this presentation will have very little to do with measurement, but lots to do with prediction. So in case you're only interested in measurement, now is your time to find a better session for you. Okay. So what this paper is, it says in the title, we're looking at human well-being and machine learning, and it's joint work with a bunch of people, as you can see, at least one of whom is in the room, and that's Katja. And then there's also Nicolo from Luxembourg, Alexander, Andrew, Jan, and Conchita, one of whom is the core organizer of this conference. And yeah, so this is joint work with all these people. And so what's our motivation to look at machine learning and human well-being? Well, in general, there's a sort of embarrassing feature of work on subjective well-being in the literature. And that is the standard models of subjective well-being explain sort of surprisingly little variance in what people answer. And there's a couple of reasons why you might think that's the case. And typically that's because when we run our regressions, so typically these are OLS regressions, or if you're being fancy, sort of ordered probit regressions, we make a couple of fairly restrictive assumptions. So you impose linearity, you impose an additive structure, so you're saying, okay, well-being is just the sum of this bunch of covariates that you have there, and typically you have only a fairly limited number of variables in your model. So that's sort of the conventional approach that we're all used to and many of us sort of practice. And then in the computer science world and social scientists are increasingly starting to use those sorts of models, the sort of machine learning approach or the algorithmic approaches, don't tend to impose those kinds of restrictions. So we don't impose additivity, linearity, and we can just throw at our models a huge number of variables. And so the question is whether those kinds of approaches can do better in terms of predicting well-being, and in terms of better explaining well-being. And to make this a little bit more precise, we sort of have two research questions here. The first one is just, are these machine learning approaches better at just predicting what people say? And the second one is whether the kinds of variables that we're identifying with these algorithms sort of agree or not with the kinds of variables that are already standardly identified in the literature. So those are the two research questions that we have. And so how do we do this? So we have three large-scale data sets, many of which you will be familiar with. So one of them is the Gallup Daily Poll covering the United States. The other one is the UK HLS, which covers the United Kingdom. And then there's the SERP, which covers Germany. The UK HLS and SERP are panel data sets, and the Gallup are repeated cross-sections. And so what we do is we have these two sort of sets of variables, one of which we call the restricted set, and the other one we call the extended set. And the restricted set just includes those variables that you would typically find in a subjective well-being model. So those variables should be sort of familiar to you. We have age squared, we have people's sex, education, income, and so on. So just these standard types of variables. And then we have an extended set, which literally includes all the variables that are available in these three data sets that aren't directly other measures of subjective well-being. And these turn out to be a fairly large number of variables. So once we code them into sort of binary dummies for categorical variables, we end up with roughly 500 variables for SERP, 1,000 variables for the UK data set, and roughly 200 variables for the Gallup data set. So this is much, much more than you would typically find in a typical model. Okay, and so how do we answer our first research question? So are we better at predicting? So first I should say we make a sort of standard assumption, and we treat well-being, our well-being data, as cardinal, meaning that the data mean the same thing across people, and the differences between response categories are equidistant. That's just to say that the difference between a 2 and a 3 is treated as the same as the difference between, say, a 4 and a 5. And then what we do is we train each of the algorithms, including OLS, on a training set. So that's just one part of our data. And then we evaluate the performance of our algorithms on a test set. So that's data that's never been seen by these algorithms. So what that means is that any of the improvements in predictive performance that I would show you are not just mechanical as a consequence of just throwing more parameters at the problem. They're in that sense genuine improvements. And then we have two sort of standard performance measures. One is the mean squared error, which is favored maybe more in the computer science literature. And then we have the R squared, which is the kind of measure that will be most familiar to us. But all our results are pretty much identical across the two measures, and that's essentially the reason for that is that the R squared is essentially the mean squared error, sort of rewritten. Okay, so this is what we're using for the first research question. And for the second research question, so where we ask, okay, which variables actually matter, we again have two sort of things that we're doing. The first is permutation importance. And that is, suppose you have a certain age, somewhere around 30, you have a certain age, I don't want to guess because then I will get into trouble, but let's say it's higher than 30. And now what we do is we just randomly assign each respondent in the survey just some other number that's also observed in the survey. So we randomly commute over the data set. And then we look at by how much the predictive performance drops as a consequence of randomly commuting. The more it drops, the more important is that variable for that model to make predictions. And then in order to find out sort of how much a variable matters in terms of like affecting well-being, we're computing these pseudo-partial effects, which is just the difference in predicted mean well-being after setting a given variable to set variables. So in the case of dummies, let's say unemployment, we first set everybody to not being unemployed, make a prediction of well-being across all the individuals in the data set, and take the mean of that. Then we set everybody to being unemployed, and again compute the mean prediction, and then we just take the difference. And that's what we call then the pseudo-partial effect of each particular variable. And in that way, we can figure out sort of what's the effect and the importance of a variable. So that's how we try to answer our second research question about what matters to well-being. Okay, so our machine learning models, or algorithms, we have essentially two, which are sort of standard in the literature, all rely on regression trees. And it takes a lot of time to explain how a regression tree really works. All I want to say at this point, and we can come back to this in case there's interest, is essentially the idea that we're just repeatedly splitting the data into lots of little bags. So suppose we split it only once, say on unemployment again. And then we take all the people that are unemployed, take their mean well-being, and take this as the prediction for all people that are unemployed. And then we take all the people that aren't unemployed and take those their mean well-being as the prediction. So this is what would happen if we only did one split. But we can repeatedly split, and there's an efficient way of doing those splits to come up with the best possible prediction given this number of splits. So this is a very high level overview of how regression trees work, but we can get into the details in the Q&A if need be. And so the two primary algorithms that we're using use these regression trees as their basic building blocks. So random forests, what they do, which is our first algorithm, is essentially we train like loads of these, or estimate loads of these trees, and then take the average prediction of all of those trees. But what we do is that each tree only has access to a certain, like a subset of all the available variables, and is based on a bootstrap sample of the original data. And the reason why we do this is because regression trees tend to like massively overfit. And so by just taking slightly different samples and then taking the average of this, we kind of get rid of this problem of overfitting. Gradient boosting is sort of the inverse of this. What we there do is we always use all of the data and we always use all of the variables, but we train like loads of very, very shallow trees where each tree improves on the prediction of the previous one. So first we have a tree, it's a very simple tree, and it makes like loads of errors. And then the second tree we'll try to predict the errors from the first tree. And then we update our prediction based on this. And then we do this a bunch of times. And when I say a bunch of times, in the case of gradient boosting, it's actually 16,000 times. So it's a long, like a list of 16,000 trees making these iterative predictions. And we compare this to the performance of OLS and Lasso, where Lasso is just a slightly more fancy version of OLS really. Okay, in terms of predictions, what we do find is that we actually do get an improvement from machine learning compared to OLS. And how you can see this, on the y-axis you've got R squared for each of our three data sets on the test set, so this is unseen data. And so in each of those cases, essentially gradient boosting and random forest improves over OLS. The improvement isn't particularly large, and it varies between data sets, where it's smallest with UKHLS, but it's there. We then do it on the extended set, so it's literally now all of the variables available. What we then get is two things. First of all of the algorithms improve, including OLS. So OLS doesn't really suffer from just throwing 1,000 variables at the problem. And we get sort of a doubling in the R squared. So instead of having now sort of 0.13, we now get an R squared between 0.26 and 0.3. And that seems to be sort of the maximum achievable with survey data. Okay. So, but what do these improvements mean? I mean, okay, you get slightly higher numbers, but what does this really mean? So what we did in order to put some meat on the bone, we compare this to the improvement we are getting from using information on health. So we run just an OLS regression without any information on health and looked what the R squared from that would be. And what we find, just as a sort of high-level takeaway from this, is that essentially the gains from gradient boosting and random forests is roughly equivalent to the gains you could be getting from using health information. So that sounds sort of more substantial, though we can debate over the practical implications of this. Okay, I know that I'm short on time, so let me just quickly talk about which variables matter. And essentially what we find across the three data sets, the variables identified by our machine learning algorithms, which have no idea, of course, about how humans are like, are identifying the same variables that we as researchers have already found in the literature to be important. So in particular, health always comes up across data set and gets roughly the same rankings across OLS versus the machine learning algorithms. We get slightly different results for the Gallup data, where sort of economic variables matter much more than in the European data sets. You might think that this is sort of a genuine cross-country difference, but we rather think that it's more likely to do with the strengths and weaknesses of the data set. And we verified this by looking at the restricted data set, where we had sort of the same variables across the data sets, and there our results were very, very similar across data sets. Okay. Another way in which we can use machine learning to validate sort of the kind of research we're typically doing is to look at the kinds of functional forms that are being identified with machine learning compared to our assumptions. So essentially what you can see here with age, you've seen the U-shape, in the previous presentations, where we just assumed sort of, okay, it's going to be U-shaped. Sometimes you get a cubic, that you get another curve. And what we can find with the machine learning algorithms that don't make a prior assumption about what the functional form is going to be, we again find the U-shape. Only that the U-shape is now slightly more kink-shaped, but that difference might be more in the details rather than a major difference or departure from the conventional literature. Okay, we did a bunch of further analyses, which we can talk about in the Q&A if you're interested. And so let me just draw sort of three main conclusions, and then I will finish. So the first one is machine learning approaches really do perform better at predicting well-being than the conventional types of linear models. And those improvements are comparable and sometimes even exceed the gains one can get from using health data in your models. Generally, we find that gradient boosting performs better than random forests. Second conclusion is that when we use all of the data that we can get our hands on, we get an R squared of 0.3. That seems to be the limit feasible with social science survey data currently. And the final thing, health, economic conditions, personality traits, and the quality of your personal relationships are identified by ML as key drivers of well-being. And those are very similar to those that we have already found in the conventional literature. In that sense, machine learning sort of validates the human-guided search for the determinants of well-being. Got some next steps. For example, we want to move to global data. We want to evaluate ML in a more causal setting. And maybe we're trying to come up with some new survey items that would be much better at doing predictions for well-being. And we're open for any suggestions about what we should be doing next. So thank you.